So in this mechanics lecture, we're going to be looking at center of mass. We're then going to consider momentum, collisions, and impulse. So if you want to read about these topics in the textbook, have a look at sections 9.1 to 9.5. So first of all, a quick recap of the most important ideas from the last lecture. In the last lecture, we saw that work done by the gravitational force on an object moving up a height h is given by minus mgh. So it's negative because the gravitational force acts down, while we've said that the object is moving up. The work done by a spring with a spring constant k as it extends from xi to xf is given by minus k over 2 times xf squared minus xi squared. And finally, we saw that we could calculate the work done by a general force, f of x, using the formula that the work is equal to the integral from the initial position to the final position of f of x dx. In the last lecture, we were looking at mechanical energy, and we said that it was conserved when non-conservative forces do no work. So the change in mechanical energy, which is equal to the change in the kinetic energy plus the change in the potential energy, is equal to 0. Now, potential energy is stored energy, so it can be calculated as the negative work done, which is negative the integral from the initial position to the final position of the force times dx. So we said the total energy, E, of a system can change only by amounts of energy that's transferred to or from the system. So if we do work on the system, then we're adding energy to it, and that leads to a change in energy, which is equal to the change in the mechanical energy, plus the change in the thermal energy, which is generally work done against friction, plus the change in the internal energy, which we'll learn more about in the thermal topic. So far, we've been talking a lot about particles or particle-like objects, but as you may have noticed, most everyday objects aren't particles. So this is why it's really useful to learn about the center of mass of a system. So the center of mass of a system is the point that moves as though all of the system's mass were concentrated there and all external forces were applied there. So let's find the center of mass for an unbalanced stick. For this stick, you can see the center of mass is just at the end of the yellow point there. So hopefully you can see that clearly. Now, if I were to throw the stick so that it undergoes projectile motion, it will rotate, but the center of mass should move as a nice projectile. So let's have a look at that. With this stick, it has been weighted, so one end is heavy and the rest is all made of wood. Okay, let's look at it as it's thrown. So hopefully in this clip you saw that the center of mass of the stick traced out a parabolic path, just like we've seen projectiles do. So we could model all the mass of this stick as concentrated at that center of mass, and then that center of mass behaves just like a normal projectile, even though there's lots of rotations and other things going on the rest of the stick. Okay, so this is just a comic that I find slightly amusing, so I'll just give you a chance to read this. Okay, so we've seen why the center of mass is so useful, but how do we find it? Well, it's physics, so there's an equation for that. So we can find the x-coordinate of the center of mass using this equation. So we've got 1 over the total mass, and then we need to sum up each of the particles making up our object. So it's the mass of each particle times the position of each particle, and if we sum all those and divide by the total mass, we'll end up with the location of the center of mass. So let's have a go at this sample problem. Okay, so in this problem we've got 3 particles. We've got x1, well, this is distance x1, and it's got mass m1, which is equal to 1 gram, and this is 1 centimeter. Now we've got m2 at x2, which is 2 grams at 2 centimeters, And then we've got 3 grams at 3 centimeters. And so the x-coordinate of the center of mass is equal to the sum of m1 x1 plus m2 x2 plus m3 x3 over the total mass, which is m1 plus m2 plus m3. So we can substitute in, we've got 1 gram times 1 centimeter plus 2 grams times 2 centimeters plus 3 grams times 3 centimeters divided by 1 plus 2 plus 3 grams. So this is grams and this is grams centimeters. And so we've got 1 plus 4 plus 9, which is 14, divided by 1 plus 2 plus 3, which is 6. So this is equal to 2.3 centimeters. So we found the x-coordinate of the center of mass of this system. So you can see it's going to be around about here, which is kind of what we expect because this one here is heavier than these ones. So you'd expect it to be closer to the third mass than the first two. So in this example problem, we're told that 70 Ophiuchi is a binary star system located 16.6 light years away from the Earth. It is in the constellation of Ophiuchius. The two stars orbit each other at an average distance of 23.2 AUs, where AU stands for astronomical unit, and 1 AU is the average distance between the Earth and the Sun, which is equal to 3.844 times 10 to the 8 meters. The heavier star, 70 Ophius A, has a mass of 0.90 solar masses, while the lighter star has a mass of 0.7 solar masses. 1 solar mass is the mass of the Sun, which is 1.989 times 10 to the 30 kilograms. When the stars are at this average distance, how far is the center of mass of the system from the center of 70 Ophius A? So to solve this problem, let's start by drawing a diagram. So here we've got our first star, which is 70 Oph A, and its center of mass we'll represent by this dot, and we'll say that that is located, we'll call it XA, is equal to 0, because in this problem we're trying to find out the distance of the center of mass of the system from this point. So this is our origin point, so this should be located at 0. And then we've got a second star over here, which is 70 Oph B, and it's got a center of mass here, and that's located at XB. And we're told in the question that this average distance between these two, which is what this is located at now, is equal to 23.2 AU. So because that's 23.2 AU from the origin, it is at x is equal to 23.2 AU. And we're told that the mass of star A is equal to 0.90 solar masses. So solar masses we can draw with this little symbol here. And mass B is equal to 0.70 solar masses. Now we are given the information in the question, so we could convert from AU and from solar masses into meters or kilometers and into kilograms, but it's not needed in this case. So we're going to save ourselves some time by not doing that. So our equation for the center of mass is equal to the sum of xi mi over the sum of mi, and we've just got two masses, 2 points in this case. So we've got XAMA plus XBMB over MA plus MB. But we said here that XA is equal to 0. So this term here, this whole thing is equal to 0. So we can write that as XBMB over MA plus MB. So now I'm going to show you why we don't need to convert the units. If you do convert the units, you won't get it wrong. It'll just take a little bit longer. Okay, so I'm going to put the units after this in square brackets. So XB is given as a distance in AU, and MB, that's given in solar masses. And then MA plus MB, both of those are solar masses. So the units for this is solar masses. So these solar mass units cancel out, and then my final answer will be in atomic units. So let's now substitute in. I've got 23.2, sorry, not atomic units, astronomical units. So 23.2 times 0.70 over 0.90 plus 0.70. And solving that on the calculator, I get 10.15 AU. So we can write this as 10.2 AU. And so along this line, it is slightly closer to star A than star B, which is what we expect, as star A is the heaviest star. So if these were going in circular orbits, which it actually turns out they're going in elliptic orbits, but if they were going in circular orbits, they both move in circles about this center of mass point here. So we've seen how to find the center of mass for a one-dimensional object, but it is also possible to find the center of mass for objects which have more than one dimension, such as 3 dimensions, like most of the objects around us. So in order to do that, we just treat each of the dimensions separately and use these same equations here to calculate the x, y, and z coordinates of the center of mass of that system. So to practice using this, for Physics 1A, try homework set 3, question 2, or for Higher 1A, also question 2. But now let's have a go at this example problem. So in this example, we've got 3 particles. M1 has a mass of 1 kilogram, M2 has a mass of 2 kilograms, and M3 has a mass of 3 kilograms, and they form an equilateral triangle with side lengths of 10 centimeters. We need to find the center of mass of this triangle. Okay, so let's put M1 at our origin. So M1 has X1 is equal to 0 and Y1 is equal to 0. Now we'll put M2 10 centimeters away along the x-axis. So this here is 10 centimeters and this is M2 and it's at location X2 is equal to 10 centimeters and Y2 is equal to 0. And then it's an equilateral triangle. So M3 is up here. So M3, which is 3 kilograms, this is 2 kilograms, this is 1 kilogram. It's up here. We'll be able to calculate this height and we'll have to do that soon. We know this length here is 10 centimeters. This length here is 10 centimeters because it's an equilateral triangle, and we've got 60 degrees here because all the angles in an equilateral triangle add to 60 degrees. So hopefully you can see that M3 has to be above the midpoint between M1 and M2. So that tells us that the x coordinate has to be 5 centimeters, and so we just need to calculate Y3. So to calculate Y3, we've got this length here is 5 centimeters and this length here is 10 centimeters. So we can use Pythagoras' theorem and write, well, 10 squared is equal to 5 squared plus Y3 squared. So that's just considering this triangle here with side length Y3, side length 5, and side length 10. And solving this, we can say, well, Y3 is going to be equal to the square root of 10 squared minus 5 squared. So this is equal to 8.66. So we can say this is equal to 8.66 centimeters. Okay, so now we need to find the center of mass. Okay, so we can find the center of mass. The x center of mass is equal to x1 m1 plus x2 m2 plus x3 m3 all over m1 plus m2 plus m3. So this is the total mass here. So we've got 0 times 1 plus 10 times 2 plus 5 times 3 over 1 plus 2 plus 3. So this is over 6. We've got 20 plus 15, 35 divided by 6. Solving that gives us 5.83. And that's centimeters, because this was centimeters times kilograms, and we're dividing by kilograms. So the y for the center of mass is equal to y1 m1 plus y2 m2 plus y3 m3 over m1 plus m2 plus m3. And this is equal to 0 times 1 plus 0 times 2 plus 8.66 times 3 divided by 1 plus 2 plus 3, which is 6. So solving this on the calculator, we get 4.33 centimeters. Okay, so if we want to give the center of mass, one way to write it is in unit vector notation. So we can say, well, the location of the center of mass is 5.8 I, where I is along the x-axis, plus 4.3 J centimeters. So let's just sketch where it is. Now this height up here is 8.66, so 4.3 is half that. So height-wise, we're exactly halfway up, which is what we'd expect because this is 3 kilograms and these two sum together to give 3 kilograms. And then we're a little bit to the right of center here. So we're around about there. And that is also what we'd expect for the x-coordinate. Because the second mass is heavier than the first one, we'd expect to be slightly closer to the second mass than the first one. Now we can also find the center of mass of a continuous object. To find the center of mass of a continuous object, we need to break it up into little components, each with a mass dm, and then sum across all of these contributions through integration. So I think it's easiest to see how to do this through an example. So in this example problem, we've got a rod. So let's sketch our rod here. And we're told that one end is at the origin, so this is x equals 0. And we're told that the linear density varies along its length, and it's described by this equation, and it's 1 meter long. So the other end of the rod is at 1 meters, x equals 1 meters. So if we want to work out, well, how much does a little increment here at a distance x from the origin, and it has width dx, contribute to the center of mass, then we'll need to use that x for the center of mass is equal to 1 over m times the integral of x dm. So we'll need an expression for dm in terms of x. So dm physically means, well, how much does this little component here dx weigh? So we can see that, well, dm is going to be equal to the density times dx. So we can substitute in the density from up here. So 2 plus 3x dx. So we can say, well, x for the center of mass will be 1 over the total mass times the integral. Now we do have the limits on our integral. We're going from x equals 0 up to x equals 1 of x times dm, where dm is 2 plus 3x dx. So this is equal to 1 over m times the integral from 0 to 1 of 2x plus 3x squared dx. So let's integrate that. We've got 1 over m times x squared plus x cubed from 0 to 1, which is equal to 1 over m times 1 plus 1, which is equal to 2 over the total mass. So now what we're going to have to do is find the total mass of this object. So the total mass of the object we get by just summing up each of the little incremental masses, so the dm's. So to do that, we need to integrate over all of dm. Now, we'll use this expression for dm here, so we'll be integrating along the entire length from 0 to 1 of 2 plus 3x dx, and when we do this we end up with 2x plus 3x squared on 2, which is equal to, and we're evaluating it at 0 and 1, so this is equal to 2 plus 3 on 2, which is equal to 3.5 kilograms is the total mass of this rod here. So this tells us that the x for the center of mass is equal to 2 divided by 3.5, which is equal to 0.57 meters. Okay, so let's just logically check that. That is around about here. Now it's getting more dense as we get further along to this end. As at this end, we've got a density of 2 plus 3, which is 5, whereas down this end, we've got a density of just 2. So we would expect the center of mass to be closer to the right end than the left end. Now we can also work out the center of mass of composite shapes. So let's consider this composite shape here, where we've got a rectangle with width W and length L and a circle with a radius R, which are joined together, and they've got a constant surface density. So let's let that constant surface density be sigma. And in this question, we're asked how far below the top of the rectangle is the center of mass of the system. So the best way to consider this is as two shapes, and then we can use, well, the center of mass is going to be equal 1 over the mass of shape 1. So we can have mass 1 times x1 plus mass 2 x2. So if we can find these for each of the shapes, then we can find it out for the total thing. So hopefully you can see by symmetry that there's a line of symmetry and sigma's constant. So the center of mass is going to be along this axis here. So what we're going to need to worry about finding is, well, how far down from this line is it? So the center of mass of the rectangle, that's going to be right in the middle of the rectangle here. So it's going to be a height L on 2 away from the top of the rectangle. And the center of mass of the circle, well, that's going to be right in the middle of the circle. So from this line up here, there's going to be a distance L plus R. So this will be L plus R. Okay, so it's only asked us to find how far below the top of the rectangle is the center of mass. So let's call this dimension down here the X dimension, and we're trying to find the X center of mass. Okay, well, to do that, we're going to need to know the mass of each of these shapes. So for the rectangle, the mass of the rectangle is going to be equal to the area of the rectangle, which is W times L times the surface density. And the mass of the circle is going to be equal to the area of the circle, which is pi r squared times the surface density. So we've now got the location of the center of mass of each of these shapes individually, and we've also got the mass of them. So we can put that into this equation. So the center of mass is at M1, which is WL sigma, times X1, which we said it was at L on 2. And then M2, that's pi r squared sigma, and then times X2, which we said was L plus R, divided by the total mass. So the total mass is the mass of the rectangle plus the mass of the circle. So that's sigma times WL plus pi r squared. So you can see that sigma occurs in every term and so is cancelling out. So we can write this as WL squared on 2 plus pi r squared times L plus R times WL plus pi r squared. So we've now come up with an expression for the center of mass. Okay, now we've seen Newton's second law so many times, but the lovely thing about Newton's second law is that we can also apply it to systems. So by that we mean that the net force is equal to the total mass of the system times the acceleration of the center of mass of the system. So you can see this is going to make the center of mass really powerful. And so the acceleration of the center of mass of the system is equal to 1 over the total mass of the system times the sum of all the masses of the little components times their acceleration. So to think about how we can use this, imagine two people standing on skateboards holding a long pole. The person on the right pulls themselves along the pole towards the right, and the system consists of the two people on the skateboards and the pole. So which of the following statements is true? There are no external net forces acting on the system, or the external forces are to the right due to the person pulling themselves along the pole, or the external forces are to the left, they oppose the motion of the person along the pole. Okay, so the correct answer to this one is actually this first one. The person pulling themselves along the pole is an internal force because they are part of the system. So anything they apply to the other members of the system is an internal force. So if somebody pulls themselves along the pole, then they will move, but the net external force is 0. So the acceleration of the center of mass of the system should also be 0. Okay, so we said that when no external forces act, then the acceleration of the center of mass must be 0, which means the velocity must remain constant, the velocity of the center of mass. So we can calculate the velocity of the center of mass using this expression here. So the velocity of the center of mass in the x direction is equal to the derivative of the x location of the center of mass with respect to time. So you can see that we can do that as 1 divided by the total mass, because that's independent of time, times the sum of the little masses, and then we've got dxi dt. And dxi dt is just the velocity of each of those particles I in the x direction. So this same equation holds in all the dimensions. So we could come up with the same one for y with a y here and the y here, and z with a z here and a z here. So that tells us that we've got a vector equation where the vector center of mass is equal to 1 over m times the sum of each of the particles' mass times their individual velocity. So we did a few demos at this point to check that this actually worked. We considered the center of mass of the skateboard systems with the pole. We also considered a couple of collision carts and what happens when there's an internal force pushing them apart. So to practice using this, if you're in Higher Physics 1A, have a go at homework set 3, question 3. So let's have a look at an example now. Okay, so in this problem, we have a car with a mass of 1.25 tons traveling at 30 kilometers per hour. Okay, so let's draw it here. So it's got a mass of this car is equal to 1.25 tons, and its speed is equal to 30 kilometers per hour, and it's going this way. Now it's rammed from behind by a second car with a mass of 2 tons. So here's the mass 2, which is 2 tons. And this one here is traveling with a speed of 60 kilometers per hour. So let's call that U2. We'll call this one U1 and this one U2. The two cars stick together. And so we're asked, what is the speed of the center of mass before the collision? So we know that the speed of the center of mass is equal to 1 over the total mass times m1 v1 plus m2 v2. And so we can say this is 1 over 2 plus 1.25. That's 1 over the total mass times m1, which is 1.25, times 30 plus 2 times 60. So this is equal to 48.46 kilometers per hour, which is equal to 48 kilometers per hour. And then in part 2, we're asked what is the speed of the cars after the collision. So since there are no external forces here, all the forces come from the second car, which is part of this system, we know that there is no acceleration of the center of mass. So the V center of mass remains at 48 kilometers per hour. And that is still equal to the total mass, which is 2 plus 1.25 times m1 times the final velocity plus m2 times the final velocity. And now they've got the same final velocity because we're told that they stick together. So we can write this as 48 point, I'll keep all my significant figures. So 48.46 times, adding these together, I've got 3.25 is equal to the final velocity, which is what I'm trying to find, times m1 plus m2, but m1 plus m2, that's just the total mass. That's what this 3.25 is. So this cancels out, and that tells me that the final speed is just the speed of the center of mass, which is the 48 kilometers per hour. Okay, so this section we're going to start looking at linear momentum. So momentum can be calculated using the formula P is equal to m times v, where v is the velocity of the object and m is the mass. So it's a vector, so you can see it's got the little vector subscript over the top, and the units can be written as kilogram meters per second or as Newton seconds. So it's faster to write Newton seconds, so maybe write it that way. So part of why momentum is useful is that it can easily be related to the forces applied to the system. So we know Newton's second law, the net force is equal to the mass times the acceleration, which is equal to the mass times the derivative of the velocity with respect to time. Now, as long as the mass isn't changing, we can put the mass up here with the velocity, and we end up with the net force is equal to dp dt, or just the derivative of the momentum with respect to time. So let's look at an example problem. So in this problem, we've got a block with a mass of 2 kilograms, which is initially traveling at 3 meters per second due north. So U is equal to 3.0 meters per second north. And we're told that a force F is equal to 1 Newton directed towards the south. So let's put that as minus 1.0 newtons, acts on the block for 10 seconds. So part 1 asks us, what is the initial momentum of the block? So we can use, well, P is equal to mv. In this case, because it's initial, we'll use the initial velocity, so we'll use mu. So this is equal to 2 times 3. And so this is equal to 6 Newton seconds, and it's a vector, so we do need to give the direction. So that's north. Then part 2 asks us, what is the final momentum of the block? So we know that F is equal to dp dt, and so we can write this as F dt is equal to dp, and so we're integrating from t equals 0 to t, and we're going from p initial to p final, and we've just calculated the initial p here. So we can say, well, F from 0 to t is equal to p from p initial to p final. So F times t is equal to p final minus p initial, which tells us that p final is equal to p initial plus the force times the time. So p initial is 6 Newton seconds north, and then we'll take north as positive, so the force, that's minus 1.0, and the time was for 10 seconds, and so this is also north. So we've got 6 minus 10, which is minus 4 Newton seconds north. Or if we want, we could write it as 4 Newton seconds south, because that's what the negative here means. It means that it's heading south. And then part 3 asks us, what is the final velocity of the block? So we can use that the P final is equal to mv final, and so V final is equal to P final over m. So this is 4 divided by 2, which is equal to 2, and the direction is south, so that's meters per second south. So let's consider the momentum of a system of particles. So if we have a system that is composed of n discrete particles, then the net momentum just comes about from the sum of each of the momentums. So that's like the net force acting upon an object is just the sum of all the discrete forces. We can do the same thing with momentum. We get that the net momentum is the sum of each of these discrete momentums, and so we can write this in symbols this way with this sum sign, and we know that momentum is just equal to the mass of the particle times the velocity of the particle, and we're summing from 1 to n. So to practice using this, homework set 3 for 1a question 1, and for higher 1a also question 1, but this is actually quite powerful. So because we have seen before that the velocity of the center of mass is equal to 1 over the mass, where the capital M here stands for the total mass of the system, which is the sum of each of the individual masses. And that's times the sum of the individual masses times the individual velocities. So you can see there's lots of similarities between these two. In fact, the only thing which is different is this 1 over m. So this allows us to write that the net momentum of a system is equal to the total mass of the system times the velocity of the center of mass. So let's have a look at why this can be so powerful. So last lecture we said that Newton's second law applies to a system of particles. So the net force is equal to the mass times the acceleration of the center of mass, where the acceleration of the center of mass is equal to 1 over the total mass times the sum of each of the individual particles' mass times the acceleration. So if we take the time derivative of our equation that the net momentum is equal to the total mass times the velocity of the center of mass that we just derived on the last slide, then we get, taking the derivative of this, the derivative of the net momentum is dp net dt, and the derivative of the mass times the velocity of the center of mass is equal to the mass times the derivative of the center of mass, but the derivative of the velocity of the center of mass is just the acceleration of the center of mass. So you can see that that is equal to the net force. So we've got that the net force acting is equal to the derivative of the net momentum. So just like we had that the force acting gave us a derivative of the momentum, this whole thing applies to systems as well as to single particles. So let's use this to solve this same problem that we solved last lecture, because it's just a slightly different way of viewing this same problem. Okay, so we've got the car with a mass of 1.25 tons. So we had this car here. Let's call this mass 1 is equal to 1.25 tons, and we've got that U1 is equal to 30 kilometers per hour. And then it's rammed by a second car here, which has a mass of 2 tons and is traveling at 60 kilometers per hour. So in part 1, we're asked what is the initial momentum of the system. So P net is equal to M1U1 plus M2U2. So this is equal to 1,250. So tons here, 1 ton is 1,000 kilograms times U1. So U1 is equal to 30 kilometers per hour, which is equal to 30 over 3.6 meters per second, which is equal to 8.33 meters per second. So this is times 8.33 plus M2, which is 2,000 kilograms times U2, and U2 is equal to 60 kilometers per hour, which is 60 over 3.6 meters per second, which is equal to 16.67 meters per second. So this is times 16.67. So solving this on the calculator, we get 43,750 newtons seconds, which is equal to 44 kilonewton seconds. Now part 2 says what is the final momentum of the cars after the collision. Okay, now the net momentum doesn't change because there's no external forces acting on the system. So because F net is equal to dP net dt, and this is equal to 0, P net must not change. So we've still got 44 kilonewton seconds, though we should have given a direction here. So in direction cars are traveling initially, because the direction they're traveling doesn't actually change. And then part 3 says, what is the speed of each of the cars after the collision? Okay, so the two cars stick together. So because the momentum's not changing, we can say, well, m1u1 plus m2u2 is equal to m1v final plus m2v final. So this tells us that v final is equal to m1u1 plus m2u2, which is just our p net, divided by m1 plus m2. That was just pulling the final velocity out as a common factor here and dividing by that. And so that is equal to 43,750 divided by 2,000, that's m2, plus 1,250, that's m1. And when we solve that, we get 13.46 meters per second, which if we want to convert back into kilometers per hour is 48 kilometers per hour. So we get the same answer as we did last lecture, but with a slightly different method by using momentum rather than the velocity of the center of mass. So this brings us to impulse. So we can rearrange our equation for the net force. So we had F is equal to dp net dt. This was also the net force. So we can rearrange this and write, well, dp is equal to F times dt. So we actually find it useful to define impulse, J, though it's sometimes written as I, as the integral of F dt. So this is the integral over time, so going from the initial time to the final time. And so combining this equation with this equation, we can see that the integral of dp with respect to time, that's integrating this side with respect to time, which just gives us the final momentum minus the initial momentum, which is just a change in momentum, is equal to the integral of f dt, which is just the impulse. So what's useful is that the impulse is also equal to the change in momentum. Okay, so we can use impulse with graphs as well. So here we've got a graph showing the force versus the time, and we have just derived that the integral of f dt is equal to the change in the momentum. So in this question, a car traveling along a straight road experiences the net force shown in the diagram. It acts in the same direction as the car travels. What is the change in momentum of the car? So we need to calculate this. And then we're asked what average force acts on the car over the time interval would result in the same change of momentum. So if instead of having this variable force, we had a constant one, what would the constant force have to be? Okay, so the change in momentum is equal to the integral of force with time. So we know that the integral is just the area under a force versus time graph. So we can start by working out this area here. So this is 2 seconds at minus 200 newtons. So this one here is minus 400. So we can say, well, minus delta P is equal to minus 400. And then we've got this triangle here, which has got a length 1 and height of minus 200. So that's minus 100. And then we've got this big triangle here where we've finally gone positive. And so this triangle is going from 3 seconds up to 8 seconds. So that's got a length of 5 and it's got a height of 1000. So plus 5 times 1000 divided by 2. And then we've got this rectangle, which goes from 8 to 10 seconds. So it's got a length of 2 seconds and a height of 1000. So that's plus 2000. So we can work out what this is. So this is equal to 4,000 Newton seconds as the change in momentum. So if I want to know, well, what's an average force would give this same thing, I can say, well, F average times T is equal to the change in momentum. So F average is equal to 4,000 divided by the time, and this was a 10-second time interval, so this would be equal to 400 newtons. So let's just check that. If we sketch on 400 newtons here, just eyeballing it, it does look like that area is similar to this area minus this area. So that seems like a fairly reasonable answer. So to practice this for 1A students, you should try homework set 3, question 3, and for higher 1A students, you should try set 3, question 4. Okay, so here's a problem to try. A paratrooper whose chute fails to open lands in snow. He is hurt slightly. Had he landed on bare ground, the stopping time would have been 10 times shorter and the collision lethal. Does the presence of snow increase, decrease, or leave unchanged the value of A, the paratrooper's change in momentum? So we've got that the impulse, force times time, is equal to the change in momentum. And the change in momentum is equal to the mass times the final velocity minus the initial velocity. Now, the final velocity and the initial velocity are not changing, and the paratrooper's mass is also not changing. So the paratrooper's change in momentum remains the same. We're then asked about the impulse stopping the paratrooper. So the impulse is equal to the force times the time, and it's the same as the change in momentum. So if the change in momentum wasn't changing here, can't be changing here either. So this one here is the same. And then the force stopping the paratrooper, well, if the time is larger, but the change in momentum is the same, then the force is going to be smaller. So the presence of the snow increased the time, and so it decreased the force. So here's another problem to try. The figure shows a ball bouncing off a wall without any change in its speed. So it's got some speed coming in and the same speed going out. Consider the change in momentum, which is delta P, in the ball's linear momentum. Okay, so we're going to consider the x direction first. So we know that the change in momentum in the x direction is equal to m times vx final minus vx initial. And when we split the velocity into x components, the x component is not changing because this speed is the same. And so we can show that initially, here's v, this is 90 minus theta because that angle's theta. So this is theta up here. So Vx is equal to V sine theta. And finally, we've got the speed going this way. This is theta, so that tells us this angle up here is theta. So this is also V sine theta. And you can see that they're both, in both cases, heading towards the right. So the change in x momentum is 0. Now, is py positive, negative, or 0? This does change. You can see this is the initial velocity and this is the final velocity. So they're equal in magnitude. They're both v cos theta, but one's going down, the initial one's going down, and then the final one's going up. So taking the positive y direction as up the screen, we've got the final velocity is up the screen. The initial velocity is down the screen. And so when we add these two together like this, we get a positive one away up the screen. So this is going to be positive if we take up the screen as positive. And so what is the direction of delta P? Well, it's just the y direction here. So it's up the screen. That's in the positive y direction. Okay, so here's this question, but now we're doing it quantitatively. So a continuous stream of balls is thrown at a wall at an angle of 30 degrees. So this angle here is 30 degrees. The balls each have a mass of 100 grams. So the mass is equal to 100 grams, which is 0.100 kilograms, and have a speed of 3 meters per second. The collisions last for 0.020 seconds. So time for the collision is 0.020 seconds. And one ball hits the wall every 0.5 seconds. Okay, so we're asked what is the impulse during each collision. So we've got that the impulse, force times time, is equal to the change in momentum. So as we were discussing last time, the x direction doesn't change. It's only the y direction that changes. So the change in the momentum is equal to the mass times the final velocity in the y direction minus the initial velocity in the y direction. And so if we split our velocity up into an x and a y component, we can see this is theta here, and so we've got v cos theta is the initial velocity in the y direction, which is equal to 3 times cos of 30, and that is equal to 2.598 meters per second. And finally, it's got the same magnitude, but it's heading in the opposite direction. So we can write this as m, and then we've got v cos 30 minus v cos 30. So this is equal to m, which is 0.100, times v cos 30, which is 2.598, and there's 2 of these. So solving that, I end up with 0.52 Newton seconds away from the wall. Okay, now part B says, what is the average force on the wall during the collision? Okay, so now we're going to be using this equation, but the time that we're doing is during the collision. So we can say, well, the average force is equal to the change in momentum divided by the time, which is 0.52, divided by the collision time is 0.020. And so this is equal to 26 newtons away from the wall. Part C then says, what is the average force on the wall? So to get the average force over all, we'll need to do the change in momentum, but the time, rather than being just during the collision now, is the time between the balls hitting the wall. So we've got F is equal to 0.52 divided by 0.50, and that is equal to 1.0 newtons away from the wall. So this we'd expect to be a lot less than this, because there's a lot of time when there is no ball applying a force to the wall. So this brings us to a really important rule for physics, the conservation of linear momentum. So because we know that the change in momentum is equal to the integral of f dt, then if there is no external force acting, if this f is 0 on either an object or a system of objects, then there can be no change in the linear momentum of the object or the system of objects. So that means that the final linear momentum must be the same as the initial linear momentum. So to have a go at using this, homework set 3 for 1A question 14 and for higher 1A question 19. Okay, so this is quite a fun problem. So we've got a disc with another kind of disc cut out of it. So the question asks us, where is the center of mass of the illustrated plate? The plate has uniform surface density. So let's let the surface density be sigma. So we can actually model this system as a big plate with a surface density sigma, and then this smaller plate on top of it with the surface density minus sigma, because this one here is then subtracting away from this surface density. So to find the center of mass, let's draw on some axes. Let's draw x-axis this way and y-axis this way. Now hopefully you can see with the y-axis it's absolutely symmetric. So we'd expect the center of mass in the y direction to be along this x-axis here, the y equals 0 line. So we're just going to need to worry about, well, where is the center of mass along this x-axis here? So let's start by working out the center of mass of this big disk with radius 2r. So x center of mass for the 2r disk is just going to be right in the middle of the disk. If we didn't have this little disk cut out here, it would just be right in the middle. So we'll call that 0 at the origin here. And we can work out the mass of this big disk. So the mass of the disk with radius 2r is given by the surface density times the area, which is equal to sigma times 2r squared times pi. So that's equal to sigma times 4 pi r squared. Now we need to do the same thing for this little disk with this negative surface density. So the x for the center of mass of the one with radius r, well, that center of mass is going to be in the middle of this disk, which is here. So that's a distance r from 0. So that's actually minus r is its location. So we'll call this one here minus r. And now we need to know the mass of this disk. And that's going to be minus sigma times its surface area, which is pi r squared. So this is equal to just minus sigma pi r squared, which is what I had there already. Okay, so now I've got two shapes, and I'm combining these two shapes to find the center of mass of that combined system. So x for the center of mass is equal to x center of mass 2r, that's this big shape, times the mass of 2r, plus x center of mass for r, this smaller circle, times the mass of r, divided by mass of 2r plus mass of r. So let's substitute in. I've got 0 times sigma 4 pi r squared plus minus r times minus sigma pi r squared divided by sigma 4 pi r squared minus sigma pi r squared. So this is just 0. So on the top I've got minus sigma pi r cubed. Oh, sorry, it's positive because we've got negative times negative. Then on the bottom, I can pull sigma out as a common factor, and I've also got pi r squared, which is a common factor. So here I've got 4 minus 1. So this cancels this cancels this, and I'm left with just 1r on the top, cancelling that r squared on the bottom. So I end up with r over 3. So that tells me that my center of mass is going to be at r over 3, which is around about here. So let's just make sure that that makes sense. We would expect the center of mass to be on this side, as this side has less mass because it's got this little disc cut out. So we can write that the center of mass of the illustrated plate is r over 3i plus 0j. So in this problem, we've got an asteroid which is initially at rest with a mass of 700 tons. It explodes into 3 pieces. Okay, so here it is initially. Let's say its center of mass is here. And after the explosion, we have a 100-ton piece moving with a velocity, with this velocity. So here's m1 equals 100 tons, and it's moving this way with 2i meters per second. And then a 300-ton piece is traveling this way. So we say m2 is equal to 300 tons, and this velocity v2 is equal to 0.50i minus 0.05i plus 1.0j meters per second. And we're asked what's the velocity of the third piece, so we need to find v3. Okay, and we can see initially it was at rest, so VCOM initially is equal to 0. And this is an internal force, so it explodes from something internal, so the VCOM final remains at 0, so it's always 0. So I can say, well, VCOM is equal to 1 over m, where m is the total mass, which is the 700 tons, which is equal to m1 v1 plus m2 v2 plus m3 v3, and these are all vectors. So we can start by working out what m3 is, because we know that m is equal to m1 plus m2 plus m3. So m3 is equal to m minus m1 minus m2, which is equal to 700 tons minus 100 tons minus 300 tons, which is equal to 300 tons. So I can say that 0 is equal to m1, which is 100 times v1, which is 2I, plus m2, which is 300 times v2, which is minus 0.50I, plus 1j, plus m3, which is 300 tons times v3. And this is divided by 700 is equal to the 0. But I can multiply both sides by 700 to get rid of that, and it still doesn't change 0. 0 times 700 is still 0. I can now divide by 100 to try and make it a bit simpler. So now I've got 2I plus 3 times 0.5, so that's minus 1.5I, plus 3j plus 3v3 is equal to 0. So looking in the I direction, my I components must all sum to 0. So I've got 2 minus 1.5 plus 3 times v3 in the I direction. So let's call that v3x. And that's equal to 0. So I can see 3 times v3x is equal to minus 0.5. So v3x is equal to 0.5 divided by 3, which is minus 0.17 I meters per second. So that's in the x direction. So I've put my little I unit vector back there. Now I can look at in the j direction, and in the j direction, I've got this vector and this vector. So those things need to give me 0. So I've got 0 is equal to 3 plus 3 times v3 in the y direction. So this tells me that v3y is equal to minus 3 over 3, which is equal to minus 1 meter per second. So I can say, well, the velocity of my third chunk of asteroid is going to be equal to minus 0.17 I minus 1.0 j meters per second. So I can just check that that makes sense. If I draw it onto this diagram, it's heading back in this direction and down here. So it's heading kind of down like that. And that would be what I'd expect. I'd expect these j components to cancel out, and this one's got a faster speed in that way, but this one here is heavier with its slower speed. So I wouldn't expect too much in my I direction, which is indeed what I end up with. I end up with a small velocity in the I direction. So this is a challenging problem. A uniform soft drink can of mass 0.140 kilograms is 12.0 centimeters tall and filled to the top with 0.354 kilograms of soft drink. Then small holes are drilled in the top and the bottom with negligible loss of metal to drain the drink. So we need a hole in the top to let the air in so that it can drain out smoothly. What is the height h of the center of mass of the can and the contents? Part 1 initially, and then after the can loses all the soda. And then what happens to h as the soda drains out? And finally, if x is the height of the remaining soda at a given instant, find x when the center of mass reaches its lowest point. So we've got a uniform soda can. So let's sketch it like this. And it's got a height, capital H, and that height is equal to 12 centimeters. And the mass of the can is 0.140 kilograms, and initially it's filled to the top with soda, so the mass of the soda in the can is given by 0.354 kilograms. And then we drill a small hole in the top and the bottom, and the soda starts to drain out. And in the first part, we're asked, well, what's the center of mass of the can when it's full of soda? Okay, now the nice thing with this problem is that it's very symmetrical. So with our can, we can assume it's got the same mass up the top as down the bottom. And so the center of mass of the can is going to be equal to half the height of the can, so h over 2. And the center of mass of the soda will also be right in the middle, because initially it's filled all the way to the top, so we've got as much mass above the midpoint as below it. So the center of mass of the soda will be, well, the height of the soda divided by 2, but initially this will just be h over 2. And so the center of mass of everything is going to be equal to h over 2. So this is the center of mass of the can times the mass of the can plus the center of mass of the soda, which will be x over 2 times the mass of the soda over the total mass, which is the mass of the can plus the mass of the soda. And so since the initial height of the soda, x, is h, we can write this as h over 2 outside of the mass of the can plus the mass of the soda over the mass of the can plus the mass of the soda. We've got common factors on the top and the bottom, so it's just h over 2. And since we're told that the height of the can is 12 centimeters, this is just going to be 6 centimeters. Okay, part B then asks us what's the center of mass once it's lost all the soda. So in that case, we've got that the ms is equal to 0. So we can use this same equation here, but now we've got that the mass of the soda is 0. So when we do that, we have that the center of mass is equal to h over 2 times the mass of the can over the mass of the can plus the mass of the soda, which is 0. And so this will be equal to h over 2, and so it's still 6 centimeters. Okay, now in part C, we're asked what happens to the center of mass, which is h. So this is h, this is h, as the soda drains out. So let's refer to this variable mass of soda as ms dash. So ms is the initial total mass of soda, and ms dash is the amount of soda that's actually in the can. So ms dash is going to be equal to the density of the soda times the volume. And we can work out the density because we're told the initial mass. So the density is equal to the mass divided by the initial volume, and so this will be equal to ms, which we've got a number for, I'm just not going to substitute it in right now, times the initial volume, and that's equal to the height times the cross-sectional area of the can. So now we've got an expression for the density here, and this volume's actually changing, so we've got ms over h a, and the volume in the can is, well, it's got a height x of soda and it's got cross-sectional area a. So these cross-sectional areas cancel out, and we've got the mass of soda, which is actually in the can, is the initial mass of soda times the height of the soda over the total height of the can. Okay, so our expression for the center of mass is equal to h over 2 times the mass of the can plus x over 2 times the mass of the soda, which is the initial mass of the soda times x on h, over the mass of the can plus the mass of soda in the can, which is given by ms x on h. Okay, so let's times the top and the bottom by 2. We'll actually times it by 2h because that'll make it a little bit prettier. So we end up with h squared times the mass of the can plus x times the mass of the soda, that's x squared times the mass of the soda, over 2h times the mass of the can plus 2msx. So this expression tells us what happens to the center of mass. You can see that as x drops from h squared to 0, then the numerator decreases, but the denominator also decreases. So it's probably easier to think about it physically. As the soda drains out of the can, the center of mass of the soda goes down, while the center of the mass of the can stays in the same place. So this is going to get the center of mass of the can and soda to drop. But then as this center of mass for the soda is going down, it's becoming relatively less important as the mass of the soda is going to 0. So eventually this mass of the soda is 0 and this term doesn't contribute at all. So it's dropping, but it's contributing less and less, which allows it to start coming back up to the center of the can. So when there's no soda left in the can, then the center of mass is back up here. So what happens is the center of mass drops and then comes back up. Okay, now part D is a bit of a challenge. What we'll need to do is look at this expression here, which we've just derived, and what we'll need to do is find out when is this a minimum. So in order to do that, you'll need to work out what dH dx is. So to work that out, you're going to need to use the quotient rule, which tells us that if we call h f of x, then this thing here we can call g of x, this thing here is h of x, then f dash of x is equal to g dash x h x minus g x h dash of x over h x squared. So we can work out what g dash of x is. That's the derivative of this thing with respect to x. So this term has no x dependence, this does. So this is 2x times the mass of the soda, and h dash of x, that's the derivative of this term here with respect to x, so that's equal to 2ms. So what we can do is substitute all these terms into this here to get f dash x, which is this thing. So this is f dash of x. So when we do that and simplify, we end up with 2h times the mass of the can times the mass of the soda x plus mass of the soda squared x squared minus h squared mass of the can, mass of the soda, all over 2h mass of the can plus mass of the soda x squared. And so to find the minimum, this f dash x has to be equal to 0. So we set this equal to 0, which means that just this bit up the top needs to be equal to 0. So we can solve for when this equals to 0. Once again, there's a fair amount of algebra. So we've actually got a quadratic equation here where this is x squared and then an x term and then a no x term. So with our quadratic equation, this thing here is RA, the thing in front of the x squared. This thing here is RB, and then this is RC, and our quadratic equation tells us that x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. So we can substitute these terms in here and then simplify it, and we end up with x is equal to the mass of the can times the height of the can over the mass of the soda times minus 1 plus the square root of 1 minus mass of the soda over the mass of the can. And we can take the positive square root, as x is the height of the soda above the bottom of the can, and that can't be below the bottom of the can, so it must be a positive number. So take positive square root. So now we have x, and then once we have x, the question actually asks us to find the center of mass, so h. So what we need to do then is substitute our expression for x, which we have calculated here, back into this expression here for h. And when we do that and simplify, we end up with h is equal to h times the mass of the can over the mass of the soda times the square root of 1 plus the mass of the soda over the mass of the can minus 1. And then we've got numbers for all these things, so we can substitute in. So we've got 12 centimeters is the height of the can. The mass of the can is 0.14. The mass of the soda initially was 0.354, and then times the square root of 1 plus 0.354 over 0.14, and then we've got our minus 1. Sorry, I left off the brackets around that. And then putting all that into the calculator, we end up with 4.2 centimeters. So if you got that one, congratulations. That was really very challenging with quite a few mathematical steps, but hopefully the physical reasoning about what happens makes sense. So here's a problem. A soccer player kicks a soccer ball with a mass of 0.5 kilograms that is initially at rest. So U is equal to 0, M is equal to 0.45. So from that we can see that the initial momentum is MU is 0 Newton seconds. The foot of the player is in contact with the ball for 3 times 10 to the minus 3 seconds, and the force of the kick is given by this expression here. And we're asked to A, find the magnitude of the impulse of the ball due to the kick. Okay, so for part A, we know that the impulse is equal to the integral of f dt. And so this is equal to 6 times 10 to the 6 t minus 2 times 10 to the 9 t squared dt. And we're going from 0 to 3 times 10 to the minus 3 seconds. So integrating this, we end up with 3 times 10 to the 6 t squared minus 2 times 10 to the 9 t cubed on 3. And this is from 0 to 3 times 10 to the minus 3. And so we've got 3 times 10 to the 6 times 3 times 10 to the minus 3 squared minus 2 times 10 to the 9 times 3 times 10 to the minus 3 cubed over 3. And solving this, we end up with 27 minus 18, which is equal to 9 Newton seconds. And it only asked us for the magnitude in this case. So part B then asks for the average force on the ball from the player's foot during the period of contact. So we've got that so we know that the average force is equal to the total impulse divided by the time. So that is equal to 9, which we've just calculated here, divided by the 3 times 10 to the minus 3 seconds, and that gives us 3,000 newtons, and that'd be in the direction of the kick, but it only asks us for the magnitude. Part C then asks us for the maximum force on the ball from the player's foot during the period of contact. So if we want to find the maximum of the force, we're going to have to find the turning point. So we'll have to do df dt is equal to 0. So taking the derivative of this, we've got 6 times 10 to the 6, and then the derivative of this is minus 4 times 10 to the 9 t. And we want this equal to 0, which tells us that t is equal to 6 times 10 to the 6 over 4 times 10 to the 9, which occurs at 1.5 times 10 to the minus 3 seconds, which kind of makes sense because that's right in the middle of this kick period. Okay, so we know when it occurs, so now we need to find out what it is. So we substitute this time into this equation here. So this is 6 times 10 to the 6 times 1.5 times 10 to the minus 3 minus 2 times 10 to the 9 times 1.5 times 10 to the minus 3 squared. And when we substitute that in, we get 4,500 newtons. So we should check that that's bigger than the average, which it is. So that looks around about right. Okay, part D, we're then asked to find the ball's velocity immediately after it loses contact with the player's foot. So we know the initial momentum was 0, and we know that the change in momentum is equal to the impulse. And we've calculated the impulse in part 1, so that's equal to 9. And so the change in momentum is the final momentum minus the initial momentum, but the initial momentum was 0. And so that tells us that the mass times the final velocity is equal to 9, and so the final velocity is equal to 9 divided by the mass, and the mass was 0.45, so we've got 9 divided by 0.45, and so solving that, we have 20 meters per second as the final magnitude of the ball's velocity. Okay, so this one's a little bit challenging. A two-ended rocket that is initially stationary on a frictionless fall law. So we know that U is equal to 0. With its center at the origin of an x-axis. So the center's here. The rocket consists of a central block C of mass 6 kilograms. So we can say the mass of C is equal to 6 kilograms. And blocks L and R each of mass 2 kilograms. So mass of L is equal to the mass of R is equal to 2 kilograms on the left and right sides. So a small explosion can shoot either of the side blocks away from block C along the x-axis. So here is the sequence. At time t equals 0, block L is shot to the left with a speed of 3 meters per second relative to the velocity that the explosion gives the rest of the block. Okay, so at t equals 0, we have that the velocity of L relative to the rest, so let's call the rest B for block, which is equal to the velocity of L minus the velocity of the block, remembering our relative velocity formula, is equal to 3.00 meters per second. And then step 2, at t equals 0.80 seconds, the right block is shot to the right with a speed of 3 meters per second relative to the velocity that block C then has. So the velocity of R relative to C is equal to the velocity of R minus the velocity of C, and this is equal to 3 meters per second, and that's to the right. This velocity was to the left, so we really should put a negative sign there to show that it's traveling towards the left this way. So then we're asked, this is sometime later at time t equals 2.80 seconds, what is the velocity of C equal to, and what is the position of its center? So to answer this question, we're going to need to make the assumption that no external forces are acting. So no external which tells us that momentum is conserved. So initially, since the speed of everything is 0, we know that the initial momentum must be equal to mass times the initial speed, which is 0. So this tells us that momentum is always 0. Okay, so let's consider this first explosion where we had the one on the left separate from the other two blocks. So we know that 0, that's the initial momentum, is equal to the mass of block L times the velocity of block L plus the mass of block C plus the mass of block R, that's these other two blocks, times the velocity of these blocks. Now we have masses, so we can substitute in the mass of L is 2. So this is 2 times VL plus mass of block C is 6 and mass of R is 2. So this is 8 times VB. Now what we can do is rearrange this equation up here. So this tells us that VB is equal to VL plus 3. So we can substitute that in here. So this is equal to 2VL plus 8 times VL plus 3, which we can write as 3 times 8, that's 24. So we've got minus 24 is equal to 2VL plus 8VL, which is 10VL, which tells us that VL is equal to minus 2.4 meters per second. So we expect it to be negative because it's going to the left. Okay, so now what we can do is calculate the velocity of blocks C and R. So the velocity of the block, which is the two of them stuck together, is equal to VL, which is minus 2.4 plus 3, which is equal to 0.60 meters per second, and that's to the right, which is what the positive sign's indicating there. Okay, so we've gotten to the end of this one, and now we have this second explosion that occurs. So we also assume that during the second explosion there's no external forces, all these forces are internal, so momentum is conserved. So we'll ignore block L now. So we'll consider the initial momentum of these two blocks just before the explosion. So just before the second explosion, we've got these two blocks which have a mass of 2 plus 6. So we've got 8 times the initial speed, 0.60. That's the initial momentum. It needs to be the same as the momentum after the collision. So that's mass of C, which the central block has a mass of 6 kilograms, times the velocity of C, plus the mass of the R, which is 2 kilograms, times the velocity of R. So this is what conservation of momentum tells us. And what the relative velocity equation tells us is that we can rearrange this a little bit and write V of R is equal to 3 plus V of C. So let's substitute in here for V of R. So we've got 8 times 0.6, which is equal to 4.8, is equal to 6 VC plus 2 times 3.00 plus VC. And so we've got 4.8 is equal to 6 VC plus 6 plus 2 VC. And so we've got 4.8 minus 6, which is equal to minus 1.2, is equal to 8 times VC, which tells us that VC is equal to minus 0.15 meters per second. So we were asked to find the velocity of block C after these explosions. And this is what we found here. The negative sign indicates that it's to the left. So we can write this as 0.15 meters per second to the left. Okay, so that was part A. Part B asked us to find the position of the center. Now we could consider the center of mass and use that to calculate it, but it's probably faster in this case to just use equations that describe the motion. So we just need to work out how fast the central block is moving and when. So at t equals 0, the central block has this speed vb, which is 0.60 meters per second, and it travels that fast for 0.80 seconds. So the displacement in the first 0.8 seconds is 0.80 times the 0.60. And then after the first 0.8 seconds, until the end of the 2.80 seconds, which is a 2-second interval, it's traveling at 0.15, so minus 0.15. So we're just doing the speed times the time for this 2.80 second time interval. And solving that, we end up with 0.18 meters. So it's traveled 0.18 meters to the right in that first 2.80 second time interval. Okay, so this is an interesting problem. In the Olympiad of 708 BC, some athletes competing in the standing long jump used handheld weights called halters to lengthen their jump. The weights were swung up in front before liftoff and then swung down and thrown backwards during the flight. Suppose a modern 78 kilogram long jumper similarly uses two 5.50 kilogram halters, throwing them horizontally to the rear at his maximum height, such that their horizontal velocity is 0 relative to the ground. So let his liftoff velocity be given by this expression, and with or without the halters. So the liftoff velocity is the same. And assume that he lands at the liftoff level. What distance would the use of halters add to his range? Okay, so let's sketch a little diagram of what's going on. So without the halters, the long jumper lifts off and follows the normal, his center of mass will follow the normal path. Now, with the halters at maximum height, which is midway through the flight, he's throwing the halters and he's throwing them backwards this way, which is going to give him some additional momentum this way. So that is shown relative to the long jumper because we're told that the halters move with 0 relative velocity to the ground. Okay, so he'll have additional forwards momentum, which is going to increase his horizontal speed for the second half of the flight. So he'll end up going an extra distance like this. And what the question has asked us to calculate is the difference in range here. Now, there isn't going to be any difference in range in the first half of the flight. So all we need to focus on is calculating the difference in range for the second half of the flight. But we do know from symmetry, because the weight force is the only thing which is working to accelerate him in the vertical direction, that he takes the same time to get to maximum height as he does to get to from maximum height to the minimum height. So let's start by calculating how long it takes him to get from maximum height to back to the ground. So time from max height to ground. But because we know that at max height v is equal to 0 and we know the initial velocity, we'll actually calculate the time from the ground to the maximum height and just assume that these are the same. So time to max height, we'll use our kinematic equation, Vy is equal to Uy plus Ayt. And so we can say t is equal to, now at maximum height v is 0, so this is 0, so t is equal to uy over ay and I've got a negative sign there. But uy, he is moving upwards at 4.0 meters per second, and the acceleration is downwards, so this is minus 9.8. So solving this, I get 0.408 seconds to maximum height, and that tells me 0.408 seconds back down as well. Now I know without the halters that the horizontal velocity doesn't change. So without halters, Vx is equal to 9.5 meters per second. So I can easily calculate the range without halters from maximum height, because that's where the difference is, by simply multiplying the time by the speed. So without halters, range is equal to 0.408 times 9.5, which gives me 3.876 meters. So I've literally calculated this distance here, and that is 3.876 meters. So now I'm going to worry about what happens when he throws the holders. Now I know when he throws the holders that momentum must be conserved because there's no external forces acting. This is an internal force applied on the holder, which is part of the system, by the athlete. So assuming momentum is conserved as no external forces act horizontally during the throw. So we'll assume momentum is conserved. So the mass of the man plus the mass of the holders times the initial velocity, which is ux, which we know is the 9.5, is going to be equal to the mass of the man plus the final velocity of the man in the x direction plus the mass of the holders times the final velocity of the holders in the x direction. So what I'm trying to find is this Vx, the final velocity. So let's rearrange this and write, well, Vx is equal to the mass of the man plus the mass of the holders times ux minus this thing, the mass of the holders times the velocity of the holders. And then I'm going to have to divide by my mass of man. So now we've got an equation and we can just substitute in. So the mass of the man is 78 kilograms. And the mass of the holders, now we were told that the mass of the holders is 5.5 kilograms, but that there's two of them. So we're going to have to double that. So mass of the holders is equal to 2 times 5.50, which will equal 11.0 kilograms. So this is plus 11. Now the initial speed of the man and the halters is just the horizontal velocity. So that's times 9.5. And now we need to subtract off the mass of the holders, which is the 11 kilograms, times the final speed of the holders. Now it tells us in the question that their horizontal velocity is 0 relative to the ground. So these velocities are all relative to the ground. This is the takeoff velocity relative to the ground. So I'm going to put 0 in for that. And then I divide by the mass of the man, which is 78. And so solving this, I get 10.8 meters per second. So now I know how fast the man is traveling as he descends. So I can get the range the same way I did here, just multiply the time by the speed. So the range with the halters is equal to 0.408, the time, times 10.8. And this gives me 4.423 meters. So I now know that this distance is equal to 4.423 meters. But what I've been asked to calculate is this distance here, the difference between them. So this tells me that difference is equal to 4.423 minus the 3.876. And solving this gives me the 0.55 meters. So he manages to go an extra 0.55 meters with the halters than without them.